Hello, good morning, class. Can everybody hear me okay?
Yep. Yep.
Great. So, I posted a link to today's video on YouTube is right at the chat. You can just go there and get started. So, I'm gonna start today's lecture, and by the end of it, we can have a discussion about the test we just had in chapter 2 and the plan for the future test. And the last one, I just had a chance to decide on that based on what is schedule given by the university. Okay. Okay. So what we're gonna do today is gonna be the second last lecture for the whole polymer physics. Time goes pretty fast, and now we're at the stage that is gonna in the wrap-up phase. So what we're gonna do today is to continue discuss what is a rubber elasticity, and how do we get what is a chain conformation based on rubber elasticity. Okay. In the last lecture, we briefly reviewed what is the second law and first law of thermodynamics influence on rubber elasticity theory, and we basically reached one of the very important conclusion how we can link the force F being applied to a rubber band be related to the enthalpy and entropy change being related to the deformation. Okay, so F is related to partial derivative of pressure temperature at a constant partial derivative L at a constant P and T. So you can get this value, and this is also related to let me start the slideshow, get it rolling. It's also related to, more importantly, entropy partial derivative to the L. So today's lecture is going to be continue to discuss about how does entropy differs for a single polymer coil being deformed. So what this means is, now imagine we have a Gaussian coil, we start to stretch it. Today's lecture we're going to discuss how this second term will be important for this force, because we go through the last lecture, we know the first term enthalpy partial derivative L will be very much constant, and then does not depend on much on the material, and does not contribute a lot in the rubber elasticity theory. So the goal is very simple: define the entropy and understand how does entropy differs when we stretch a single polymer coil to a longer and longer distance. This is where we roughly stopped in the last lecture. Here is where we begin to discuss and see what is relatively contribution in terms of force, which is defined by stress, or it can be generically written as force. Okay, with elongation. What does elongation means is where this is basically stress strain curve. Okay, elongation 0 is equal to elongation 0 is related to initial state, and the more you deform, the longer elongation is. There is two components here. First is basically this is force. F is what you typically measure in an instron if you do a stress strain curve. So this particular curve, which I circled, is your stress strain behavior for your rubber band. So if you think about something you made in polymer, you can just go down in our mechanical testing lab, make a dog bone coupon, load it in the instrument, and get something like this. What is more interesting for polymer scientists, in particular this lecture, is how we can differentiate this value using the internal energy, which is related to the enthalpy and entropy. It turns out to be the internal entropy U is not particularly relevant at a very large elongation. When your delta S is you can look at magnitude, this versus this is getting smaller and smaller and less important. In a long time, to simplify this to simplify the treatment of those real polymer, people just use very simple assumption that your delta U dependence on L will be negligible and can be ignored. Okay. It is pretty much the case at the large elongation. As you can see at the large elongation, the entropic contribution typically dominates in the force. And this is what we see in a rubber material. It's called a entropic rubber. So let's also talk about the rubber. One of the conclusions we know is rubber is very unique compared to metal. We have discussed that a rubber, if we stretch it and load something on the bottom of it, if you start to increase the temperature under the load, so you still hang your material on the bottom of the rubber band. When you heat it up, your rubber band is going to contract. This is usually the case. But in some of the non-ideal cases, your rubber band could still expand. So this is something people saw called a thermoelastic inversion. It's not that critical, but I want to mention in this class. So when you see some of the rubber band is being heated and expanded, don't panic. Your theory is still whole. It's just one of the unique cases that it will show this unusual behavior. And why this has happened? This is where when you stretch a different degree of strain, as shown on the data on the right. So if you look at stress and temperature, at very low stress, at very low strain, 3%, you would get very low stress, because stress strain curve is what we see. If we go back, 3% strain is probably this is elongation is too low. Let me redraw just a generic stress strain curve. Stress, strain, this is what it typically is. So if you have at very low strain, you're going to have very low stress. And the more you go up, you have higher stress. Okay, that's why at 3%, 13, and 38%, you have higher and higher stress, as indicated on the axis on the left. Now, what this thermal inversion means, typically what you would see is on the top, where increase the temperature from, let's say, 0 degree to 80 degree, that's the bottom axis, you would actually found your rubber band has increased in your in the stress level, where initially it could be somewhere about 2.9, and this value could go up all the way to there, maybe somewhere 3.3 and 3.4. And this is very common. This happens at multiple strains, as you can see, but at very low strain, so for example 3 or 6%, there's not much increase. As you can see, your stress is more or less stable. And this is turned out to be related to the elastic force. It is related to the internal energy. Okay, the internal energy of the like what I said in here, it's relative. Here you have at low strain your entropy and internal energy delta U is on a similar level. So here, one of the other component is going to come in play, is where you now start to need to worry about another phenomenon, is called thermal expansion. When your material is being heated, it thermal expands. It's related to the internal energy. So now it's a competition between the internal energy and the elastic force. So if we go back, in this equation, we basically at low strain. These two values are on a comparable magnitude. So we no longer can remove the entropy term and only look at the entropy term. Okay. It's one minor effect, but you should know that at low strain it will behave slightly different. So now let's focus on the entropy term, and we talked about entropy is going to be the dominant force in determining your force in the rubber band. Now the question is, how do we get the entropy for a single chain? And how do we relate this single chain's entropy to our rubber band? It turns out we did a lot of homework already in the first chapter. If everybody recall, time has been a little bit while since we discussed this chain conformation. I hope your memory is still fresh for the September's lecture. So we talked about a Gaussian coil. We talked about chain end distribution. For a Gaussian coil, if we fix one end at the origin of the axis, then the other end it will be predicted by distribution of end chain end. Okay, this distribution probability basically can be captured using this particular equation, as we discussed before. We have a normalization factor or constant, which is where I highlighted. This is a prefactor, and if we have a defined n and a b, this will be a constant, right? And we have exponential value or exponential term on the other hand, where it depends on exponential of minus 2/3 of r squared divided by mv squared. We know mv squared will again be a constant, so your chain end Gaussian distribution is really dependent on r value. I'm not going to repeat too much, but we pretty much know this is going to behave like this, right? So now, coming back to the topic, so if we explore what we know, then chain end distribution is one thing. Now, how can we convert this distribution probability to entropy is going to use another equation we know. It's uses entropy will be equals to Boltzmann constant log of omega. Here, the omega, again, is related to the number of conformation state available to a polymer chain, like we show here, okay? So in here, we need to consider two variants. One is the chain length, the other is end-to-end distance. Those two values going to define what the entropy is, okay? So I think we get a pathway forward if we can combine the Gaussian coil and those conformation theory together with the equation particular here to get delta S. We can actually get a pretty good results to predict what is the force for a rubber band. Okay, and this is done early days by several scientists, and notably back in early as before the Second World War, or around Second World War. You can see the name is again Flory and Rayner did it in 1942, and Wall did it in 1942. Okay, so it's just 1 year apart, but they both were able to treat the data to get the final results. But one of the assumptions they have to do is to something called affine network. So note the words affine, A-F-F-I-N-E. So affine means your results is deformation, macroscopic deformation is attached to local microscopic deformation. What that means is if I stretch a rubber band twice the length, we assume at the single coil level, the 2 times deformation is being felt by this tiny polymer coil, and it will deform accordingly. And affine, you can think about if you stretch a rubber band, if you pin 2 of the other material to that, how long the rubber band stretch, you'll find the network will stretch the same, okay? There's a couple more assumptions related to how we can treat within these crosslinks or within these affine network. That are the network initially need to be isotropic. So when you make the rubber band, it cannot be non-isotropic. This is assumption related to how we can use a Gaussian coil. If it's non-isotropic, then we need to worry about in the stretch direction versus the perpendicular direction to the strand, because you cannot no longer use the same treatment assuming it's a Gaussian coil. That you can still calculate, but it will really complicate all your calculation, makes your results rather complicated. And for the sake of discussion in today's lecture, we don't need to go that route, and we can just keep it simple, okay? So your system is going to be isotropic. That means there is no deformation in the coil before we stretch it. And second is the segment between those crosslinks, and usually if you want to get a rubber material, you need to have a crosslinks, okay? Like natural rubber is cross-linked by the sulfur, and these crosslinks are going to allow you to have permanent covalent bond within the network. So your polymer chain going to be have multiple crosslink points along its backbone. So this segment basically says chain segment between the crosslinks will still obey the Gaussian coil statistics. So your single chain from the chain beginning to end will obey the Gaussian coil. But even after crosslinked, we say that with each segment, between each crosslink point, it still do the same. And that's actually pretty much the case. And you can make this assumption easily and without worrying it's going too far away, okay? The last one is the volume is constant during deformation. This is we call it ideal elastomer, and you have a Poisson ratio of equal to 0.5. In this scenario that you will see later, it is important for us to understand what's the deformation in the deformation direction in the stretch X versus the deformation direction in the Y and Z, because the Poisson ratio will be used here to predict the ADAs to predict the force as well. Okay, so with those assumptions laid out, the next step is basically apply what we know in the entropy relationship in the chain and distribution and get what it is for entropy for a different state of the single chain. We just need to simply combine these two equations, and this is what you would get if you do that. You would get this particular equation. So S will equal to K. K is going to be Boltzmann constant and 2/3 log n. This is the initial constant that is before we call it normalization factor, right? Because it doesn't depend on R, so no matter how far you deform your coil, this is always going to be fixed value. But the second term, R value, is dependent on degree of deformation. So this is going to be changed as long as we stretch the coil. And additionally, people also could rewrite the equation before to two values. First is R0 square. This is end-to-end distance square. That's what we use to say equilibrium R0 value. And second is where we call it the R value, displacement R vector square. We're gonna deconvolute it into three terms: x, y, and z. That's the three dimension in the x-axis where their value are. Because once we stretch them, we're gonna likely, if we stretch in the x direction, we're gonna increase in x but decrease in y and z. So it's important for us to break down this r square absolute term into three-dimensional x, y, z term. And this is where you will see in the later part of the lecture that the assumption is ideal elastic. There is no change in the volume going to come into play. We can link x, y, and z. Okay? Yeah, pretty much like this. So the first term, because it's a constant, so we can just write as a constant value. And the other term, you can basically write as 2/3 of the k, right here, 2/3 of the k multiplied by 2r0 square and x, y, z square. Okay, So once again, this is Boltzmann constant. This is end-to-end distance at equilibrium. So if you don't stretch it, it's your initial r squared. And it's equal to mb squared. N is a degree of polymerization. B is statistical segment length. And xyd is where the deformation degree for your material. Okay, so now we know what is entropy for a single chain. So now to get what is the rubber elasticity theory, I'm gonna write the copy the equation here one more time. So F is going to be dependent on temperature and entropy partial derivative of L. Okay? So I'm going to write this particular equation. So this is important that we need to understand what is entropy before and after deformation. We can't just use one state, so that's why we need to consider a theoretical polymer coil that is shown initially looks like blue, and it's drawn on a 3-axis in our 3-dimensional space. So initially it's at R0, and R0 is located exactly where the end of this vector is, and it has a coordinate of x0, y0, z0. And after deformation, we stretch in the x direction. Your coordinate will be shifted to a new r that will define a new x, y, z where this new chain end is. But the origin is fixed where it's both at 0. So what can we do now? We can apply what we have learned in the last slides to understand what is entropy at blue state at R0 to the end state at R. Okay? So this is what you would get. Delta S will be a constant where these two are basically the same constant. When they subtract each other, they're going to cancel out. What left is where 2r squared and 3kr f initial. Okay. And you're going to take away the others. Sorry, this is actually should spell as final. This is the initial, okay? Again, when conversion in the PC to Mac, there is a little bit issue. final, initial, okay? So this is what you're going to get if you apply this two. So that means this is going to be the final state. This will be the initial state. And R0, you know, is these. And what left is really x, y, and z square. So we now going to further go down the mass treatment to understand how can we link these x, y, z with x, y, and z0. Here is where the rubber incompressibility parameter can come in. First, we know the deformation we can basically apply as strain will be final L minus initial L, or basically dl divided by L0. Okay? We now can assume use a fine network. This is what we mean. Initially, it's a cube. When you deformed it, the degree of deformation is going to be equal to lambda z in LZ0. So that means how much expansion in the z direction in the extension ratio or jaw ratio this lambda is. And a fine network basically says if you zoom in the microscope, you would look at a single coil. If you zoom in the deformed case, you will look at another coil. These two are both deformed, so they're going to change. If we know that generically we can define three jaw ratio value in the x and y and z direction, that's why you see you get x0, lambda x, lambda y, lambda z, and initial length x, y, z, 0, and your final value. So this is nothing fancy, it's just a square of each term. So now we know the delta S is basically going to be equal to final value lambda x square minus 1, y0 square, lambda y0 square lambda y square minus 1, and the z0 square lambda z square minus 1. And this is nothing but a definition of what these lambda values are and apply to this particular equation. Because these are going to be equals to lambda x0 square. Recall that you have a minus term here, and this is going to be x0 square, so that's why it's become lambda x square minus 1 and x0 square, okay? Because there's a minus term. If you apply this repetitively to 3 different directions, that's what you would get. Okay, so we know there is incompressibility, and in the next slides we will talk about lambda x, lambda y, and lambda z will be equals to 1. Incompressibility basically says your volume will be constant, okay? Right here. And we're going to come back to these slides once we talked about. Let's first discuss about the affine network, how we can understand this in terms of network strain. So the entropy change for the whole network is going to be the sum of all the entropy change with the network with n strand. What this means is, this is talk about if you have a rubber band, there's going to be many cross-link points. There are going to be many parts of molecular is being deformed. So all we need to do is just to sum up all the deformation in the x and y and z direction. And this is what we're going to do here is to discuss what happens in 3-dimensional deformation. So here we need to sum up all this. Sometime is going to be used to discuss in the material system in a single rubber band how many there's n bonds, then there's n cross-link point, then there's going to be n contribution of each deformation entropy, okay? So in the isotropic states, that's where it's important is in initial states you would have the same x0, y0, and z0, and this is where we wrote in here x, y, z will be the same before we deform it, because we have basically isotropic states. And we know that here it's going to be isotropic state, and this final distance here is going to be r0 square. So this is just a simple math and geometry. You know that if you add x0, y0, and z0 square will be equals to r0 square. Why? Because x, y, z are the coordinate in x, y, z direction. If you want to have the diagonal of a cubic, you're going to be equals to, in the square of each side. So x square, y square, z square will be equals to the diagonal r square, okay? Using those two equations, isotropic state, and we know that initially they 3 add together will be r0 square, we can easily get each term is x0 square, y0 square will be equals to 1/3 of nr0 square, or equals to mb square divided by 3, okay? So n again is number of strands in the system. Strands is basically says the piece between the cross-link points. So it's just an additive number. The higher the cross-link density, the n will be higher. Okay, so this is proportional to just how strongly you cross-link the system. mb square is basically the end-to-end distance equal to this r0 square, so, and divide by 3. All right, so if we now apply what is x0 to the original equation, we can basically cancel out this mb squared term with this mb squared term. They're the same. They're going to cancel out. Once this 3 will be also be cancelled out with this 3. So what really left you for the network of the entropy in the system is going to be equals to n number of strands. Okay, so that's related to degree of cross-linking. K is a Boltzmann constant divided by 2. Remember, 3 is already cancelled with this particular 3. mb squared is also cancelled out with mb squared at the bottom of the original equation. So that's all you have left. This is, again, a very ideal network, but it's very good for our discussion. We wrote 2 different minor difference equations. The difference is one we wrote as n, the other we wrote as VE. And this is come to one reality that for the real polymer chain, there's always cross-link defects. There's some part of strain is not contributing as much as the other. So that's why we need to have an effective term come into play here. Okay, that's where the VE is. That's the effective cross-link network density versus your cross-link density in general. And for now, we just need to focus on the equation in the box. Let me repeat it one more time. Your entropy in today's lecture, we know, relate direct proportional to number of strands and number of degree of strain in our rubber band. Okay? And everybody knows what is lambda x, lambda z, lambda x, lambda z square is, right? So that's just the formation in 3 different directions. And minus 3, where does 3 come from? 3 comes from, we need to have a lambda 0. So if you add those minus 1, minus 1, minus 1, that's where the minus 0 is, minus 3 is. Okay? So we can add one more simplification to the equation. What we have discussed is apply incompressibility assumption. This assumption basically says when you stretch a material in the x direction, the y and z direction will shrink at the value of 1 divided by lambda x. Okay, so in this way, you could have a constant value like we show here. Lambda x, lambda y, lambda c will be equal to 1. That means there's no volume change before and after stretch. Okay, so this allows us to basically replace all the lambda y and the lambda z in the equation we saw before. So if we replace these to lambda x, we could get a simplified equation as shown on the right. Or we can just call it in lambda, because we only stretch in one direction. So the entropy of the network is very simple. It's going to be proportional to n, how heavily you cross-link your system, and lambda square plus 1, 2 divided by lambda minus 3. We know what these two, how about where does this come from? This comes from the lambda x, lambda y square divided by, it's okay, don't move. This comes from lambda y square. Remember, this was originally was lambda x square plus lambda y plus lambda z square minus 3. So lambda x square basically is converted to here. Lambda y square, as we know, lambda y is now equals to half of lambda x. So this is basically 1 divided by lambda plus another 1 divided by lambda. Okay? So if we combine these two, that's where you got the second term is 2 divided by lambda is where it comes from. So quite nice and simple. We got really made a lot of progress today to get what is entropy relation with respect to the degree of deformation. So lambda degree of deformation. So you can see S increases quite largely when you have a very large lambda, because lambda square will grow very exponentially. The second term shows your entropy will drop in the other direction with proportional to 2 divided by lambda. You know, this is inverse of 2 lambda, so your entropy will drop. So it's a competition of these two to determine what is the final entropy. Okay? And now apply back to what the force term is, where we know the force is, we discussed at the beginning, your stress is something you can measure, but not the entropy. So we need to convert the entropy to the force. F will be equal to minus T, entropy divided by L, and this is what you would have. Lambda term, we need to get what is the lambda with respect to the L, and convert this L to delta lambda. Delta L, delta lambda relationship is quite straightforward. It's just related to where the original L0, okay? So, here you go. We apply this particular entropy term into here. This is what you would get. You would get this is what the force of deformed coil is going to be proportional to nkt. What is n? Number of strands in the network. K is Boltzmann constant. T is temperature. L0 is a fixed term. Take a partial derivative to the lambda, so this going to becomes 2 lambda, and 2 cancel out each other with first, so you get lambda basically, and minus the 2 divided by lambda. Take a partial derivative, 2 lambda will be equals to what do you show here, and the constant, take a partial derivative to the lambda will go away. So in other words, now we can get a stress in relationship with your degree of deformation lambda for ideal network. What you can see is how does this force will depend on the lambda. It's not directly linear to the lambda, but it's quite close at high strain. But you could also have the lambda square term on the bottom. Okay, that's the difference with a hook coil. The spring, it follows a Hooke's law, going to be just a linear relationship between the force and displacement. It also depends on n, the force. N is number of strands, so the higher the crosslink, the more tougher, more stronger your rubber is. And we could also see from the entropy theory, your force is now proportional to the temperature. That's why we showed at the beginning our material is very different with respect to a metal, because now you can see the higher the temperature, the stronger the rubber band is, the force, okay? This is the origin of that. So for this tensile deformation, it's quite easy to understand. There's one more thing I'm going to cover in this particular part is where now you can also discuss the value of the stress. Stress is basically force divided by area, so you can calculate out what the force is. It's going to be, I don't go into too much detail. Again, this is where your original force is. You need to divide by the area, and you can convert the area to what you have known as the L0, Y0, and that will give you the V. V is the volume of your initial state, and the difference is you got a one additional lambda here. Remember, the force is only dependent, linear dependence to lambda, but now strain is dependent lambda squared. Why is that? So this comes back to what is the Ly and Lz is. So when we need to link these Ly and Z to L0, so Ly is after deformation what your L is. Remember, this is going to be linked to lambda y L y 0. This is final states of L, this is initial states of L, and this is what the lambda is, the deformation. So if you combine all these together, that's what you would get. If you multiply the lambda y and consider here, you also have a lambda z term, you can get what the value is. These two combined will give you another lambda term, okay, as shown here. This defined as the true stress in a material system, so how the true stress depends on the value. And you could also have engineering stress, is where you engineer and divide by initial value. So this engineering and true stress, as we know, they should only differs by a factor of lambda, which is the case right here, okay? We can also link your stress and strain to get the Young's modulus. Young's modulus will be defined with this particular equation, and you can also get the other values related to them. The other value is G value, is where the shear modulus related to the network. Okay, so note one thing differs with what we show is where now we have n kt divided by v. Again, this is a modulus. N is cross-link density. K is basically a Boltzmann constant. T is temperature divided by v. We can also simplify the first two terms. N divided by v is talk about how many density of crosslink within a certain volume. And it turns out to be this can be related to mx. And we're going to talk more in the next class. But this nx is basically the molecular weight between the crosslink points. So in other words, so if you have a network, you can count how many crosslink points. This is one way you know how heavily crosslinked. The other is basically look at how much distance between these two coils are. So this is called crosslink molecular weight, mx. If this mx is low, then you have much higher modulus. If the crosslink density is high, then you would have a very low mx. If the crosslink density is low, that means crosslink density is far away, then you would have larger mx, okay? So with that, we're going to wrap up today's lecture. I think we did quite a lot. We have pretty successfully talked about how we can link the entropy of the single chain to the force, the stress, as well as the force for a rubber band. And as you can see, this is a great example. We can explain what happens at the molecular level and how you can link the cross-link density at the molecular level deformation to macroscopically force and stress. Okay, so I'm gonna stop the broadcast, and I'm gonna answer questions anyone have on the Zoom.